This Stephenson 2-18 star is a red hypergiant about 19,000 light-years away from us, the largest star we know in the universe. It has a diameter exactly 2,150 times that of the Sun and a volume 10 billion times greater. In other words, if we wanted, we could fit a full 10 billion suns inside this star. Or think of the giant stars among the brightest we see in the sky: Betelgeuse, Antares, Aldebaran, Arcturus. Even all of those giants are quite small next to the Stephenson star. Even so, we still struggle to compare the Sun with the sizes of these stars. When we make the comparison this way, it becomes inevitable to get the impression that the Sun is a tiny, insignificant speck of dust. These are, of course, true. The Sun really is very, very small next to the giants we listed and more, as if we barely exist in the universe. Let's admit it, the striking comparisons in popular science documentaries about how tiny the Sun looks against other stars may have thrown you into existential crises or shaped your views of the universe. But is it really so? Is our star, the Sun, truly a small star? Today, when we take not a superficial but a somewhat deeper look at astronomy, you'll discover how our ideas about our place in the universe change, and how your mind pushes you to think in completely different ways about this. This is the Hertzsprung-Russell, or HR, diagram. This diagram should be the first thing that comes to mind when we say astronomy, because it is an indispensable tool for determining the life cycles of stars and understanding how they are classified. In other words, we can call this the periodic table of astronomy. Just as the periodic table is vital in chemistry, the HR diagram is that vital for astronomy. Without the HR diagram, it's impossible to understand stars. On the diagram's horizontal axis, we see stellar temperatures. On the vertical axis, we see radiative power. Radiative power and brightness are not the same thing, but for now, we can think of it as brightness. So according to this diagram, the hottest and most radiatively powerful stars sit in the upper left of the diagram, while the coolest and least radiatively powerful stars sit in the lower right. At the same time, on the horizontal axis, we can also see the types of stars. For example, according to the diagram, M-type stars are located in the lower right of the diagram. We can say these stars are relatively cool and red. For example, Proxima Centauri, which we know as the closest star to us after the Sun, sits in the lower right region of this diagram. So where is the Sun, our star, on this diagram? The Sun is a G-type yellow dwarf star. Compared to other stars, it has almost average temperature and average brightness. In that case, we can see that the Sun sits roughly toward the middle of the HR diagram. That is, according to the diagram, the Sun's luminosity is neither very high nor very low. With a surface temperature of 5,772 Kelvin, it has an average temperature. And in size as well, we can see it has an average scale. Indeed, based on all this, we can say the Sun is an average star. As you can notice, even at this point, just by looking at the HR diagram, we already see that the Sun is not as insignificant and small as the comparisons at the beginning of the video suggested. Because according to the diagram, there are many types of stars that are much dimmer, much smaller, or much shorter-lived than the Sun. We've already shifted the Sun from the small star status to the average status. But what you're about to learn will surprise you even more. To understand whether the Sun is a small star, there's a critical question we must ask. As we move toward the lower right of the HR diagram, we see stars smaller than the Sun. As we move toward the upper left, we see stars larger than the Sun. Also, in the thick band running across the HR diagram, we call the stars their main sequence stars. During their evolution, stars spend most of their lifetimes here, that is, in the main sequence phase. In other words, for the vast majority of their lifetimes, stars are busy fusing hydrogen into helium. We can consider this their healthy phase. For example, our Sun is currently a main sequence star. Precisely because of this, because stars spend most of their time in the main sequence stars constitute 90% of the stars in the universe. However, if we look at the diagram again, we see that stars much larger than the Sun, like Bellatrix, Sirius, Spica, also appear as main sequence stars. So to compare other stars with the Sun correctly, the real question we must ask is this: what percentage of main sequence stars are of which types? In earlier videos on this channel, I've said many times that the lifetimes of stars are directly related to their masses. I'll emphasize it again here. The most important criterion determining how long a star will live is the star's mass. As mass increases, the increased gravitational pull causes the star to consume its fuel more quickly. For this reason, high-mass stars live short lives, while low-mass stars live longer. In other words, when it comes to stars, the live fast, die young principle applies. This simple rule causes low-mass stars to be more numerous in the universe. For example, in our galaxy, an overwhelming majority, 85%, of stars are M-type red dwarfs. Because while giant high-mass stars quickly burn through their fuel and die, red dwarf stars continue to live calmly for long periods. Over time, that causes the red dwarf population in the universe to increase. Therefore, the proportion of M-type red dwarfs we see in the lower right corner of the HR diagram is 85% higher than other stars in our galaxy and in the universe. This means the following. In fact, it's not very reasonable to compare the Sun with supergiant and hypergiant stars, because those giants make up only a very small fraction of the stars in the universe. In other words, the giant stars we see in popular science documentaries or in those online videos comparing star sizes, Stephenson, Scutum, Betelgeuse, Antares, at most make up 5 or 6% of all stars. That is, the star we think of as tiny next to other stars, our Sun, is larger than at least 85% of the stars in our galaxy, and larger than 80% of all the stars in the universe. Moreover, not only in terms of size but also in terms of mass and luminosity, the Sun is a bigger star, and we're not talking about a small margin. The red dwarf stars we're talking about are so small that their sizes can be comparable to gas giant planets like Jupiter. When we look at the issue from this angle, we grasp this. Far from being as small as it's often portrayed among all stars, the Sun is in fact much larger, much brighter, and much more massive than 80% of all stars in the universe. What's more, because in stars' mass and lifetime are directly related, the fact that the supergiant stars we mentioned at the beginning of the video are much shorter-lived than the red dwarfs, which are the numerical rulers of the universe, is often ignored. For example, even the highest mass red dwarf stars have lifetimes of tens of billions of years. Don't forget that the age of the universe itself is 13.8 billion years. That is, these stars have lifetimes at least as long as the age of the universe. Lower mass red dwarfs can live for trillions of years. Ironically, the stars we tend to overlook because of their low mass and faint light, the red dwarfs, will in fact continue living even after all other stars, including the Sun, are long gone, and eventually they will be the last stars to persist in the universe. In short, among all stars, far from being as small as it's often said, even the expression that the Sun is an average star is debatable. So what do you think? By calling the Sun a small star, aren't we being unfair to it?